earlier, it's time to get straight down to the implementation part, which we're going to use my favorite deep learning library, PyTorch, for. Okay, cool. So first of all, before I start with going through the code and explaining how it works and how we solve the problem, just a little note about this competition in particular and why this approach is so useful. So like I mentioned earlier, this is the Quora Insincere Questions Classification competition, which was hosted on Kaggle back in late 2018. And the winner of this competition, the Zoo, is an amazing team, right? And they managed to win the competition with an F1 score of 0.713 on the private leaderboard. And this was actually a big margin win, because if you look at the second team, wasn't able to even reach 0.713. But the Roberta model, which I'm going to demonstrate now, actually scored 0.714 on the private leaderboard. But in this particular competition, no pre-trained models like BERT or Roberta were allowed, even though transformers existed at that time. The competition had an official no external data, no internet rule, which did not let participants leverage the power of these pre-trained models. And this submission of a score 0.714 did not require any specific tuning or pre-processing or anything like that. It was my first simple naive submission with Roberta base. So it's amazing what we can do with fine-tuning and massive transformers like Roberta, even beating the top team who took 2 to 3 months to build this pipeline. It really shows the power of pre-trained neural networks. Okay, so since we have an idea of the power of transformers now, let's get to exactly how the code works. Okay, cool. So here I have all the code for this Roberta fine-tuning pipeline on a Kaggle kernel, right? So I will actually link the code in the description below. You can just click on that link and you'll go straight to the code here, the kernel on Kaggle, which has all the fine-tuning logic. Okay, and as usual, I run all my PyTorch models on TPU. So all you need to do is go to settings and enable the TPU onto the accelerator section, so that your models run as fast as possible. Okay, so let's get started. Let's get started with the code walkthrough. Okay, so what's the first step? The first step is to set up PyTorch XLA. So for those of you who don't know, PyTorch XLA is basically PyTorch but on TPUs, right? Google's TPU, which is a specialized hardware built for deep learning and AI, and it can run orders of magnitude faster than CPUs and GPUs, and that's why we're going to use it in our project today. So PyTorch XLA is specifically built to run PyTorch on these tensor processing units. Okay, and this particular line of code here, all it does, as you can see here, curl, it says curl and a specific URL. It basically loads up the setup code from the PyTorch XLA GitHub repo. So as you can see, this .py file here, envsetup.py, contains all the Python code necessary to set up PyTorch XLA for TPUs in our environment. So by running this code, we're basically getting that setup code from the PyTorch XLA repo. So just run it here. Okay, looks like it ran successfully, which means we have the .py file with all the setup code. Now the next line of code says Python PyTorch XLA envsetup.py. So all this does is it's basically running the setup code that we got here from this cell, right? It's basically running the setup code and setting up PyTorch XLA in our Kaggle kernel. So once this finishes running, we should hopefully have PyTorch XLA and TPU set up on our Kaggle kernel environment, which is pretty awesome. So let's get started. Okay, so it says this may take around 2 minutes. So I guess we need to be a little patient. But once it's done, We have PyTorch XLA completely set up and we can run our models on TPU. Okay, looks like it's working successfully. And one more thing I forgot to mention earlier was make sure you switch on the internet setting here under the Kaggle kernel settings, otherwise this won't work, because for TPUs to work on Kaggle, we need to retrieve setup code from the GitHub repo of PyTorch XLA and a lot of other things. So without switching on the internet connection, none of this is going to work, so make sure you have it on when you run the code. Okay, looks like it's running successfully. It says installing collected packages, torch, processing the nightly wheels. Installing Torch XLA. This looks good. As expected, it's taking a little bit of time. Guess we need to be a little patient with this. Okay, cool. Looks like this cell of code has finished running. And what that means is we have PyTorch XLA successfully set up on our Kaggle kernel environment, which is awesome. Okay, cool. So the next step here is to export XLA use bf16 equals 1. So I'll just explain this a bit. So when Google launched the TPU, right, the TPU comes built in with this special new data type called bfloat16. Okay, so bfloat16 is this new sort of tensor data type which Google came up with, and it offers the representational capacity of float 32, right? Maintains a representational capacity of float 32 while having the computational overhead of float 16. So it's basically like a sort of mixed precision data type which offers the power of float 32, but it's easy to process like float 16. So the result is very fast processing without giving up much on the accuracy. So you're still able to have a similar representational capacity and a similar model accuracy and performance while getting massive gains in training and inference speed. And this is why Google came up with BF16 when they launched the TPU, right? So when we say export XLA use BF equals 1, we're basically explicitly saying that we want PyTorch XLA to make use of bfloat16 to speed up training and inference. Okay, cool. So now since we have exported this, we should have much faster training, right? And when we say pip install colored, so colored is basically this package, Python package, which allows you to print colored text in Python. And this is very useful when you're printing complex training logs or anything like that. It makes everything much easier to read, and that's why we're using colored. Okay, cool. So since we have everything installed, okay, I'll just run this cell of code. Since we have everything installed, all we need to do now is import all the necessary libraries that we need to run our Quora Roberta fine-tuning pipeline. Okay, looks like installation is done. Okay, so as you can see, these are all the standard libraries for machine learning here at the top. You can see OS garbage collector, GC, time for keeping track of training times, colored for coloring the text, NumPy and pandas obviously, and matplotlib for data visualization. And here at the bottom you can see a lot of PyTorch and Torch XLA imports, right? all the standard PyTorch imports for data loading and modeling, neural networks, etc. And these 3 Torch XLA imports you can see here will help us run our models on TPU. Okay, cool. So I'll just run this piece of code. It should import all the necessary libraries for us. And also, if you notice, we have these couple of imports at the bottom here, which are also very important. From transformers, import Roberta model and Roberta tokenizer. So transformers is basically this library which is made by HUGGINGFACE. Okay, so for those of you who don't know about HUGGINGFACE, it's this amazing company that builds excellent open source tools for natural language processing, especially deep natural language processing with transformers. So definitely check out their website. They have a lot of cool tutorials and demos on deep NLP with transformers. Okay, so that was just an aside. And getting back to the code, so from transformers import Roberta model and Roberta tokenizer. Roberta model is basically the Roberta model architecture with all the pre-trained weights, so that we can start with our pre-trained model and fine-tune it later. And Roberta tokenizer is basically this utility that helps us parse our text into tokens, which helps our model read the text. I will talk a little bit more about tokenization later, which I did not touch upon much in the previous section. Okay, and these 2 Keras imports, 2 categorical and pad sequences. So 2 categorical helps us convert our targets into categorical format, and pad sequences helps us pad our tokens to a particular length, because every single question in our Quora dataset is of a different length. Like, for example, one comment could have just 2 words, I like something random. Something else could have like 50 words. So we want to kind of bring all of them to a certain constant length, so that our model can actually vectorize these operations and perform matrix multiplications easily. Because if you do not have a constant token number, constant token length, then we cannot pass all these questions in large batches to Roberta. We will have to give them one by one, which we do not want to do. That will be too slow. So we kind of pad all these question texts into a certain length, like 50 or 100. So that's what pad sequences does. Okay, cool. So now the next step after importing all the libraries is to define hyperparameters and load the data. So as you can see here, we have some key hyperparameters, the number of epochs to train. This is max length. This is what I was talking about when I was talking about Keras tokenizer. So every single question in the text is going to be brought down to a token length of 64. So each one of these is of size 64, right? Okay, cool. So that's the max length I've chosen. Max length can be anything, but for this particular project, we choose 64 because most questions do not have more than 100 words, usually more than 100 tokens. Okay, split equals 0.8. This basically gives us the percentage of data that we want to use for training. Here 0.8 means we want to use 80% of the data, which is 80% of those 1.3 million comments for training, right? 80%. Okay, sorry. 80% for training, right? And we want to leave aside the other 20% for validation. So this is training and this is validation. Validation is basically unseen data that's kept away from the model, so that we can use this data to evaluate the model's performance on unknown or unseen data in the future, right? And 80% of the data is the data which the model trains on. Okay, and drop rate, this is basically dropout, which helps the model generalize to unseen data more easily. You can search more about dropout online. It's basically this simple mechanism which randomly drops neurons from a fully connected layer in order to train all the neurons together properly and reduce overfitting, right? And these are the learning rates of the different layers, right? 4e minus 5 is for the Roberta layers, and 1e minus 2 is for our custom dense head. So if I go up back to what we were talking about before, right, remember we have Roberta here, RB, and we have a dense layer. So we want Roberta to have a small learning rate like 4e minus 5, right? And we want the dense layer to have a larger learning rate like 1e minus 2, because the dense layer is completely untrained. It's initialized with random weights, but Roberta is already fine-tuned on a lot of text. So we don't want to mess around too much with its weights. We just want to tune it a little bit, very finely. But the dense layer needs to be adjusted heavily to ensure good performance. And that's why we want different learning rates for the Roberta model and for the dense head on top. Okay, so batch size and val batch size. Batch size of 256 means we'll be passing batches of size 256 for training, and a batch size of 8192 for validation, right? A bigger batch size for validation, because in validation we do not have backpropagation, right? We're not training on the validation data, and that's what allows us to use much higher batch sizes without running into memory issues, because there are no gradients being computed when you're doing validation. Okay, and this is the path at which we're going to save our trained model at the end. It's called insinceritymodel.pt. We're going to be training the PyTorch model and then saving it. Okay, cool. So next step here is to set random seeds, right, for NumPy and PyTorch. This makes our model reproducible, and it makes sure that every time you run the code, you get the same results, right? Without setting the random seed, it's actually very difficult to share your results with other people and replicate them. So just set the random seed, and now we load the training and testing data frames, which have all our Quora questions which we're going to train on. Okay, so this is the test data frame here. All right, it has a unique ID and question text. We don't care much about the unique ID, but we do care about the question text. Trained DF, on the other hand, has the question ID, question text, and a target, right? So we're going to build a model that takes this question text as input and outputs the target, which is 0 or 1, right? These are just binary targets here. And obviously the testing data frame doesn't have these targets, because the testing data frame is meant to make predictions on and not for training, right? So this is our entire data set. And if you check the length of the training data set, right, it's more than 1.3 million. So we have 1.3 million comments to train our Roberta model on, which is a lot. And that's why we're able to get such good results, because we have so much data to train on, right? But if you look at len of test df, we can see that there are approximately 375,000 comments in our testing data frame. So we have 1.3 million testing questions. 1.3 million training samples to train our model on, and 375,000 comments to make predictions on, right? So this is the data, and so the next step here is to define something we call a PyTorch dataset. Okay, PyTorch dataset. The PyTorch dataset is actually the core of the data loading process in any PyTorch pipeline. So what we're going to do is we're just going to build this PyTorch dataset, which will help us load the data and actually feed batches of data into our model for training. Okay, so as you can see here, our dataset has 3 separate functions. One is called init, one is called len, and one is called getItem. So these 3 functions have very simple functions. Very simple tasks. So what init does is it just initializes a bunch of instance variables specific to that particular object, which is the dataset object, right? So self.text equals data.questionText. So as you can see, the init function here takes data and tokenizer as input, right? Tokenizer is basically this simple, you can think of it as a simple function that takes a question, right? Let's say we have a question and converts it into a bunch of tokens, right? So let's say we have I am happy. I am happy, right? It can encode one, I can encode I as 1, am as 2, and happy as 3. So it's basically converting this text into a bunch of numbers which Roberta can understand. So every pre-trained model, including Roberta, BERT, etc., has its own tokenizer. So the tokenizer actually goes hand in hand with the model. Every model has its own tokenizer. For example, BERT may encode the word am as, let's say, 35, just an example. But Roberta may encode the same word am as 105, right? So we have to use the correct tokenizer for the correct model, right? So this is a tokenizer which we're going to pass into the init function when we're actually initializing the PyTorch dataset. So self.text equals data.questionText. This basically contains all the questions in the data. Self.tokenizer equals tokenizer. You can see this here. We're basically initializing the tokenizer for our dataset. And this final line looks a little complex, but what it's doing is very simple. Self.target equals data.target. So like I mentioned before, data is the data frame which we're passing in. So data.questionText gives all the questions. Data.target actually gives all the targets, which are zeros and ones. So data.target if target in data.columns, else -1 into len of data, right? So we know that the testing data does not contain any targets, right? The testing data does not contain any targets, and that's why the target column isn't present in the testing data frame. So data.target if target is in the data frame columns, else just output a bunch of -1s as the targets, which are basically a bunch of dummy targets which we do not need to care about, right? So this basically initializes the targets for a data set, which is going to be the actual targets if it's the training phase. But for the testing or validation phase, right, we don't really care about the targets because we're not doing any backpropagation. For the testing, for the validation phase, we actually need the targets to calculate the score, right, the validation score. And that's why we use data.target for training and validation, and -1 into len of data for testing. Okay, cool. So the next function is also very simple. Len basically outputs the total length of our PyTorch dataset, which here is len of self.data, right? This basically gives you the total number of data samples in our dataset and the total number of indices on which our total number of indices on which our dataset can iterate over, right? Len of self.data. And get item, this is what does the bulk of the work. Okay, so this might look a bit complex, but I'll just walk you through the basics of what's happening. So this is where the tokenizer does its work. So as you can see here, target equals self.target I, right? This is basically just getting the target at the ith index. So what get item does, right, the get item function, it outputs the feature, target pair, okay, the feature target pair at index I, right? So you have a particular index I, right, in your data set, and you want both the input and the output at that particular index, right? So the output is basically target, which we are seeing here, target equals self.target I, but the input is actually this massive vector of tokens, right? This massive vector of tokens. So now let's talk a little bit about how this input, which is a vector of tokens, is actually generated. Okay, So, okay, so now remember we initialize a tokenizer in the init function with self.tokenizer equals tokenizer. This is the same tokenizer we're using here. So when we say self.tokenizer.encode, right, all it's doing is taking this question, okay, it's taking question, as you can see here, self.tokenizer.encode question. It takes the question text and outputs a vector of tokens. So like for example, it might take I am Tarun, okay, I am T, okay, and output 1, 5, 7, okay, and Roberta knows that 1, 5 and 7 represent I, am and T, right? And you can see the simple dot strip here. All that does is it removes the trailing and ending spaces of the text. So if you have string space blah 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 close bracket close quotes, it'll remove this extra unnecessary space at the beginning because we don't need it. So that's all strip does. So we just strip the question and encode it into a bunch of tokens, right? And as you can see here, there's a bunch of lines of code that generate something called an attention mask, right? Attention mask, okay, so basically how Roberta works is it gets a bunch of tokens, right, like 1, 2, 3, okay, and let's say there's this token, some special number, let's say 50, okay, 1, 2, 3, 50, 50, 50, or just let's say 250s, okay. So remember I specified earlier that we use Quora's pad sequences to bring every single question in our text down to the same length, right? So what Roberta expects is it expects this attention mask, which is basically a bunch of zeros and ones, okay, zeros and ones, okay, bunch of zeros and ones that tells Roberta on which parts of the sequence to focus on and which parts it doesn't need to focus on, okay. So what Quora's tokenizer does is it takes all these sequences, okay, like let's say we have sequence 1, 2, 3, okay, and we have sequence 1, 2, 3, 4, 5, okay, and we want to pad both of these sequences to the length 5. So the second sequence is already of length 5, but the first sequence becomes 1, 2, 3, 0, 0, where 0 represents a simple padding token. A padding token is basically just a token that's added at the end of the text, at the end of the tokens, to indicate that just to fill up the space so that we can bring up the sequence to max length, right? So these zeros basically just bring up this vector of tokens to max length. But Roberta does not know that these tokens are unnecessary, right? It doesn't know that these two zeros do not matter and they're just padding tokens. So what we need to do is give an attention mask with ones and zeros specifying which positions to focus on and which ones not. So 1, 1, 1, 0, 0. Okay, this is an example of an attention mask. So we put ones at the positions where we want Roberta to focus, and we put zeros where we want it to ignore, right? So it does not look at these two last, you see these two last tokens here, which are basically padding tokens to fill up the space. Since max length is 5 here, we have these two last tokens to fill up the space and make it equal to 5 tokens. So since we have two zeros here at the end, right, Roberta will just ignore these last two tokens because they land at the 0 positions, which means Roberta doesn't care about that, right? And these 3 tokens at the beginning, which are actual words or actual tokens in our sequence, are recorded and processed by Roberta because we have ones at these positions in the attention mask. So the attention mask is very important because it tells Roberta which tokens in the sequence to pay attention to. Since we are using this entire padding thing which basically cuts few questions and pads few questions to a higher length, we need to tell Roberta in some way that, okay, this is a token that you need to focus on, and this is a token that's just there to fill up the space, right? So this attention mask is a way of telling Roberta which token is just there to fill the space and which token is actually representing something, okay? So that's what this attention mask here is. You can see attention mask, right? And I wrote a bunch of lines of code to actually put the ones at the non-padded tokens and put zeros at the padded tokens, right? And one more thing I forgot to mention is Roberta has two tokens. One is called the start of sequence. I think it's called SOS, start of sequence, and end of sequence tokens, right? So the start of sequence token is basically a 0 and the end of sequence is a 2. So what that means is when Roberta sees a 0, it knows that the sequence is starting, and when it sees a 2, it knows that the sequence is ending. So what we do is we take our entire random bunch of tokens 1, 2, 3, 5, 7, 9, blah blah blah. We put a 0 at the beginning and a 2 at the end. Why? Because when Roberta gets these tokens as input, it's expecting a 0 at the start of a sequence and a 2 at the end of the sequence, right? So this is just the format that Roberta is expecting, and I've just written this simple line of code here to insert a 0 at the end. Insert a 0 at the start of the sequence and insert a 2 at the end. So that's all this thing does. It takes the question at ID 1, okay? It takes the question at index I and it tokenizes the text, right? Tokenizes the text, then it pads the text. It pads the text to a certain maximum length, which in our case is exactly equal to 64, right? 64. And then it adds a 0 at the beginning and a 2 at the end, along with an attention mask. So that's all getItem does. It does all this bunch of processing, tokenizing, padding, all these pre-processing steps needed before we input these tokens into Roberta. And it obviously outputs a target at index I as well. So just to summarize it, getItem, we'll just call it G here. It gives the model input and the model output at index I. So at a particular index I, it gives the input and output. The input is basically this bunch of random tokens which represent our question, right? It's just a bunch of random tokens. And out is basically a binary target which is 0 or 1. Okay, cool. So now since we have an idea of how our dataset works, let's get to the tokenizer part, okay? So these two lines of code basically just initialize the tokenizer for us, the Roberta tokenizer. Okay, so basically what just happened here is we loaded the pre-trained Roberta tokenizer from the HUGGINGFACE library. It gets us this encoder function which takes the text, the question text as input and outputs a bunch of tokens. And we're later going to use this tokenizer to initialize our datasets. Okay.